Recall the Fibonacci sequence. It starts off 0, 1, and from then on, you get the next term by adding together the previous two. It isn't very hard to compute, but if you want to, say, compute the 100th term, it may seem like too much effort, because you have to compute all 99 preceding terms first. Finding a formula would solve this problem for us. As a start towards a solution, we will take the somewhat strange step of considering the power series whose coefficients are the Fibonacci numbers, which we will call f of z. We can abbreviate the sum as shown, where f sub n is the nth Fibonacci number. At first, it seems like we've done nothing. All we have done is attached a z to the n to each Fibonacci number. However, now we can view the Fibonacci sequence in an entirely new light. Our goal is to use this framing to reverse engineer the coefficients of the power series, and hence the Fibonacci sequence itself. Let's consider the expression f of z plus z times f of z. We write out each power series and distribute the z. This increases the power of each term by 1, so to add these together, we shift over z times f of z. Then, adding up the terms, we get a somewhat familiar looking series. The coefficients are Fibonacci numbers. And this should make sense. At all but the z to the 0th term, we've added together two consecutive Fibonacci numbers, so we should expect to see another Fibonacci number. However, this isn't exactly the original series. We're missing one of the 1s, and everything is shifted over by 1. We can subtract z from the original series to account for the missing 1, and dividing by z will reduce the powers back to where they are in our new sum. Then, we see that f of z plus z times f of z is equal to f of z minus z all over z. After doing some mild algebra, we discover that f of z is equal to negative z all over z squared plus z minus 1. We could choose to stop here and give an alternative way of calculating the Fibonacci sequence. Since f of z equals this function, we can take a Taylor series centered at 0 to find its coefficients. However, we can actually take this a step further. We do a partial fraction decomposition to write f of z as 1 over the square root of 5 times the quantity 1 over 1 minus phi times z minus 1 over 1 minus 1 over phi times z, where phi is the golden ratio. Observe that each of these fractions is in fact the sum of a geometric series. A little more algebra, and we have found that the coefficients of this power series are 1 over the square root of 5 times the quantity phi to the n plus phi to the negative n. But remember, the coefficient of z to the n is f sub n, the nth Fibonacci number. Then f sub n is equal to 1 over the square root of 5 times the quantity phi to the n plus phi to the negative n. So, using nothing but tools a Calculus 2 student should be familiar with, we have managed to find a formula for the nth Fibonacci number. The so-called generating function for a sequence a sub n is simply the power series where the coefficient of z to the n is a sub n. Generating functions were developed by de Moivre specifically for finding formulas for linear recurrences like the Fibonacci sequence. However, as is all too common in math, once a tool is introduced, mathematicians run wild with it. The title of this video is Counting with Calculus, and in particular we will be using generating functions to count things. As an example of something we might want to count, consider binary trees. These are rooted trees where every vertex has 0, 1, or 2 children. We call the children the left child and the right child. We distinguish between these children, so we consider these trees to be distinct from these trees. We want to count the number of trees with n vertices in total. There is only one binary tree with 1 vertex. There are 2 binary trees with 2 vertices, 5 binary trees with 3 vertices, and so on. There are 14 binary trees with 4 vertices. If you want, pause the video and try to draw them all. In order to count these and similar objects in general, we introduce the concept of a combinatorial class. A combinatorial class is a set of objects equipped with a size function to the non-negative integers such that there are only finitely many objects of each size. It is convenient to think of an object of size n as having n atoms, where atoms carry the size of the object. In the previous example, our size function is the number of vertices in each tree, so we should think of the vertices as the atoms. We will call this class T. As a simpler example, we could consider the non-negative integers themselves, with the size of an integer equal to itself. In this case, counting is quite easy. There is one integer of every size. We will call this class n. To bring this under our atom analogy, I have depicted each integer n as a line segment with n bullets in it. Since this doesn't quite make sense for 0, we depict the 0 element with the Greek letter epsilon. As a perhaps even simpler example, consider the class that contains only one object having one atom. We will call this class Z for a reason that will make sense very soon. It will also be convenient to have the class epsilon, which contains a single element of size 0. For class A, we have an associated sequence a sub 0, a sub 1, etc., where a sub n is the number of objects of weight n. We also have the associated generating function, where the coefficient of z to the n is a sub n. As a useful convention, we use a script capital letter for the combinatorial class, a lowercase letter for the sequence, and a regular capital letter for the generating function. So the generating function for script A is denoted a of z, with coefficients a sub n. Observe that the generating function for the class z is just the series z, which is where the name comes from. Let us consider two ways of building combinatorial classes out of other combinatorial classes. Perhaps the simplest, and most obvious, is to add two classes together. We define the sum, a plus b, to be a new class whose objects are all the objects in A and all the objects in B. One concern that we should have is if A and B contain some of the same objects. In order to not have to deal with this, we will always consider A and B to have nothing in common. An easy way to think about this is we color all of the objects in A orange and all of the objects in B blue. That way, A and B have no objects in common, and A plus B is all orange and blue objects. This is also known as the disjoint union. The plus notation is suggestive here of what occurs on the level of generating functions. It should be clear that the number of objects of weight n is just the sum of the objects of weight n in A and the objects of weight n in B. Then the generating function of script A plus script B is simply A of z plus B of z. The next way of building combinatorial classes out of others is a little bit more subtle. We define the Cartesian product of A and B to be all pairs of objects with the first entry coming from A and the second entry coming from B. The total number of atoms in a pair is the sum of the atoms in the first entry and the atoms in the second entry. It turns out that the generating function of A times B is precisely A of z times B of z. I encourage you to think about why this should be the case. Let's consider an example. The generating function for n, as used before, is equal to 1 over 1 minus z. Now suppose that we want to count how many pairs of non-negative integers have sum equal to n. The class P of pairs of non-negative integers is equal to n times n, so the generating function for P is 1 over 1 minus z squared. This is the derivative of n, so P of z is equal to n prime of z. So, there are n plus 1 pairs of non-negative integers that sum to n for each integer n. this is a good time to observe what multiplying by z does to a combinatorial class. This simply tacks on an extra atom to every object, so it increases the weight of everything by 1. Likewise, to a generating function, this simply increases the index of each term by 1. We also see that multiplying by epsilon pairs each object with a single object that has no weight. I like to think of this as having a ghost haunting each object, as there is ostensibly something there, and yet it adds no weight. This does not change the generating function whatsoever. As a far more interesting example, consider T, the class of binary trees. We can describe each tree as a root vertex paired with nothing, just a left subtree, just a right subtree, or both a left and a right subtree. Then in the language of combinatorial classes that we've developed, we have T is equal to Z times epsilon plus T times epsilon plus epsilon times T plus T times T. Translating this to generating functions, we have T of Z is equal to Z times the quantity 1 plus T of Z times 1 plus 1 times T of Z plus T of Z squared. Then after some mild algebra, we get Z times T of Z squared plus 2Z minus 1 times T of Z plus Z is equal to 0. And by the quadratic formula, we have T of Z equals 1 minus 2Z plus or minus the square root of 1 minus 4Z all over 2Z. Then we have determined that T must be one of two functions. Let's graph them. In blue on the left, we have 1 minus 2Z plus the square root of 1 minus 4Z all over 2Z, and in orange on the right, we have 1 minus 2Z minus the square root of 1 minus 4Z all over 2Z. Power series are continuous at z equals 0, so of the two options, plus or minus, we see that we must choose minus. And boom! All we did was write down a description of what binary trees look like, and like magic, we found its generating function. The formula for the coefficients of the power series expansion for this starting at n equals 1 is t sub n equals 2n factorial all divided by n plus 1 factorial times n factorial. See if you can show this by repeatedly taking derivatives. This is a special sequence known as the Catalan numbers. Let's consider another example. This time, we will once again consider binary trees, but now where each vertex only has 0 or 2 children. Once again, we want to distinguish between the left and right children, so that we do not have to worry about overcounting mirror symmetries. These are also known as full binary trees, so we will denote the class of them by f. We can describe any full binary tree as being a root followed by either 0 or by 2 full binary trees. Then in the language of combinatorial classes that we have developed, we have f equals z times epsilon plus f times f. Then translating to generating functions, we have f of z is equal to z times 1 plus f of z squared. After a little algebra, we get z times f of z squared minus f of z plus z equals 0. And applying the quadratic formula, we find that f of z is equal to 1 plus or minus the square root of 1 minus 4z squared, all over 2z. Once again, we must choose the function with the minus to avoid a non-removable discontinuity. If we recall the generating function t of z is equal to 1 minus 2z minus the square root of 1 minus 4z all over 2z, then f of z looks suspiciously similar. Indeed, if we pay close attention, we see that f of z is equal to z times t of z squared plus z. This tells us exactly what the power series for f of z looks like. Other than the first term, this is just z squared substituted into the generating function for t, and then shifted over. This tells us two things. First, that there are no full binary trees with an even number of vertices. This much should be obvious. The more astounding fact is that full binary trees with an odd number of vertices are also counted by the Catalan numbers. There are many ways of building combinatorial classes out of other combinatorial classes. However, for the sake of time, we will look at just one more. This last one is known as the sequence operator, which we will abbreviate as seq. We take a combinatorial class and we count all of the finite sequences made up of its elements, including the empty sequence. From this definition, we can see that this is built up out of our two earlier constructions. That is, seq of A is equal to epsilon plus A times A plus A times A times A, and so on. We've actually already seen the sequence operator in action. The natural numbers n are equal to seq of z, as we could represent each natural number n as a list made up of n ones. And in fact, this is how I did so visually earlier in the video. There is a potential issue with this construction. There may be infinitely many objects for a given weight. In particular, if there is an object with weight 0, then each time that object is paired with itself however many times, this sequence will have weight 0. Then there would be infinitely many objects of weight 0, an issue for our definition of a combinatorial class. Thankfully, this is the only way this issue can arise, so we can avoid the problem entirely as long as we forbid applying a sequence operator on a class that has objects of 0 weight. As with our previous constructions, the sequence construction has a corresponding meaning for generating functions. As we might expect, seq of A of z is equal to 1 plus A of z plus A of z squared plus A of z cubed, and so on. Now for any particular value of z, this is just a geometric series with ratio A of z. Furthermore, since we require that script A has no objects with weight 0, A of 0 equals 0. Since A is continuous, this tells us that for sufficiently small values of z, A of z is less than 1. Then we have that seq of A of z equals 1 over 1 minus A of z. Indeed, in our earlier example, n equals seq of z, and the generating function n equals 1 over 1 minus z. As another simple example of the seq operator, suppose we want to count the number of ordered partitions of each integer n. That is, we want to find out how many ways an ordered list of positive integers can sum to n. For example, there are 8 ways to add up to 4. The class of non-negative integers is given by n, so to get the class of positive integers, we can simply add 1 to each integer. Then the class of positive integers is z times n, and we are looking for sequences of positive integers. Then we want the generating function of seq of z times n, which is equal to 1 over 1 minus z over 1 minus z. After some algebra, we see this is 1 plus z over 1 minus 2z, which is 1 plus z times the geometric series with ratio 2z. Then for n greater than or equal to 1, there are 2 to the n minus 1 ordered lists of integers that add up to n. For our last example, we will count ordered trees. We will call this class omega, both to stand for ordered trees, and because this is our final example. These are trees where each vertex has any number of children, but we do care about the order in which the children appear. That is, there is a first child, a second child, etc. We can describe ordered trees as a root, followed by nothing, 1 tree, 2 trees, and so on. In other words, this is a root followed by a sequence of trees. Then we have omega is equal to z times seq of omega. Translating to generating functions, we get omega of z is equal to z over 1 minus omega of z. After some algebra, we get omega of z squared minus omega of z plus z equals 0. Applying the quadratic formula, we find that omega of z is equal to 1 plus or minus the square root of 1 minus 4z all over 2. This time, both of our choices for functions are continuous at 0. However, when we plug in 0 through z, we get that the positive option gives us omega of 0 equals 1, and the negative option gives us omega of 0 equals 0. Omega of 0 is the constant term of the power series, and as every ordered tree has a root, there are no ordered trees with 0 atoms. Hence we must take the negative option. And, well, this is quite the surprise. Once again, we get the generating function for the Catalan numbers. We really get to see the magic of generating functions from these examples. By nothing more than writing down the structures of these various objects, we've managed to count them almost instantaneously, and see that they are all counted by the same sequence. In choosing these examples, I did cherry-pick them to be counted by the Catalan numbers. However, I didn't have to look too far, as there are over 200 different classes known to be counted by them. When I first saw this technique, I was absolutely blown away. I think this is mathematics at its finest. The idea to make a sequence the coefficients of a power series is pretty simple, and yet it yields a tremendously powerful combinatorial technique. I hope you enjoyed this video, and if you have any questions or comments, please let me know.